Welcome back to ILLUSTRON. This is the first video in our new machine learning series. Today, we'll dive into the fundamental concept of linear regression. Linear regression is a powerful tool that helps us understand relationships between variables. Whether you're a data scientist, engineer, or simply curious about the world, understanding linear regression is a valuable skill. In this video, we'll explore the core concepts of linear regression, from the simple line equation to the optimization techniques that make it work. By the end of this video, you'll be able to understand the basic principles of linear regression, visualize the learning process of a linear regression model. In future videos, we'll delve deeper into practical applications and implementation techniques. Let's get started. Now that we've embarked on our machine learning journey, let's dive into the core concept of this video: linear regression. Linear regression is a statistical method that helps us model the relationship between two variables. Imagine you're a teacher trying to predict a student's final grade based on their study hours and attendance. Linear regression can help you find a linear equation that best explains how these factors influence the final grade. We will focus on the univariant linear regression model in this video. This equation, represented mathematically as f of x equals wx plus b, captures the essence of linear regression. Here, x represents the independent variable, study hours, w is the weight or slope of the line, and b is the bias or the point where the line intersects the y-axis. Think of the weight, w, as the importance of study hours in determining the final grade. A higher weight indicates that study hours have a greater impact on the final grade. The bias, b, represents the baseline grade a student might get even without studying. Now, let's visualize the model itself. This blue block represents the linear regression model. It takes the input feature, study hours, and transforms it into a predicted output value, the final grade. So, how does linear regression work? It goes through a series of steps. First, we provide the model with training data, which consists of pairs of input values, study hours, and their corresponding actual output values, final grades. The model then attempts to draw a best fit line through this data by initializing the weight, w, and bias, b, with some starting values. The model evaluates its performance by comparing the predicted output values, y hat, with the actual output values from the training data, y. This comparison helps us understand how well the model captures the relationship between study hours and the final grade. Finally, the model employs an optimization algorithm to adjust the weight and bias in a way that minimizes the difference between the predicted and actual grades. This process helps the model improve its accuracy and fit the data better. By iterating through these steps, the linear regression model learns to make increasingly accurate predictions for new students' final grades based on their study hours. In the next section, we'll explore how to visualize this learning process in action. Now that we understand the core concepts of linear regression, let's explore the data we'll use to train the model. Imagine we have a dataset for predicting student grades based on study hours. This data likely comes from past student records or similar sources. This table represents a sample of the training data we'll use. Each row shows a student's index, their study hours, and their corresponding final grade. The complete dataset contains 100 such data points. But this table shows a representative sample to give you an idea of the information available. Now, Let's visualize this data on a coordinate plane. This is our coordinate plane, with study hours on the x-axis and final grades on the y-axis. Each green dot represents a data point from the training set. As you can see, there's a positive correlation between study hours and grades. However, there's also some scatter due to factors beyond study hours that might influence final grades. The model will analyze this data to learn the underlying trend and create a best fit line for predicting future grades based on new study hour values. Remember this equation that represents the model, where W is the weight and B is the bias. Initially, we can assign some starting values to these parameters. Here, we've set W to 1 and B to 1. Based on these values, the model generates a best fit line with a slope of 1 and y-intercept of 1, shown in white, through the data points. So, what do you think? Does this line accurately capture the relationship between study hours and grades? Don't worry, our model isn't crying just yet. It's clear that this initial line isn't a perfect fit. There are significant deviations between the line and the actual data points. In the next section, we'll see how the model learns from its mistakes and improves its accuracy. We saw that the initial model didn't perfectly fit the data. How can we quantify this imperfection and guide the model towards a better fit? This is where the cost function comes in. It's a mathematical tool that measures how well the model's predictions, the estimated output values, deviate from the actual data points. In this case, we'll use a common cost function called the squared error cost function. Let's break down this equation. J of W and B represents the cost value for a given set of weights, W, and bias, B. M is the total number of data points in the training set. The summation part, sigma, iterates through all data points. For each point, it calculates the squared difference between the model's predicted value, y hat of I, and the actual data value, y of I. Finally, we average this squared difference across all data points using 1/2m. So, a higher cost value indicates a larger overall deviation between the model's predictions and the actual data. Look back at the data points and the initial model line. Y equals x plus 1. We can calculate the cost function for these initial values of W and B. Both 1 in this case. These red lines represent the difference between the predicted and actual values for each data point. This table shows a sample of these differences squared for the first few data points. The cost function considers the average of such squared differences across all data points. We can calculate the actual cost function value for this initial model using a formula. In our case, the cost function value is quite high, indicating a significant difference between the model's predictions and the actual data. This high cost motivates the model to improve its fit and reduce this difference. In the next section, we'll explore how the model uses this cost function to learn and get better at predicting grades based on study hours. We saw that the cost function helps us quantify the model's imperfection. Now, we need a way for the model to learn and improve its fit based on this cost. This is where gradient descent comes in. Gradient descent is an algorithm that finds the optimal values of the parameters W and B for the best fit line to minimize the cost function, J. To achieve this, gradient descent uses the concept of the derivative. The derivative tells us how much a function changes at a specific point. In our case, we'll use the derivative of the cost function with respect to the weights. W and B. Let's explore the mathematical representation of the gradient descent. We have two updating rules. One for updating W and the other is for updating B. W new represents the new weight value after the update. W old represents the current weight value. Alpha. This is the learning rate, a parameter that controls the step size the model takes. Partial differential J, partial differential W, this represents the partial derivative of the cost function. J. With respect to the weight. W. It tells us the steepness of the slope at the current weight value, W old. Essentially, Rule 1 subtracts a fraction of the derivative from the current weight, pushing it in the direction of steeper descent. Similarly, Rule 2 adjusts the bias based on the derivative to minimize the cost function. By repeatedly applying these update rules, the model iteratively adjusts its weights and bias to minimize the cost function, leading to a better fit for the data. This process continues until the model converges, meaning that the changes in the weights and bias become negligible, and the derivatives approach zero. To control the pace of this learning process, we introduce the learning rate, alpha, a positive value that determines the size of the steps the model takes in each iteration. Small learning rate. A smaller learning rate leads to smaller steps, resulting in a slower but more stable convergence. It's suitable for complex problems or noisy data. Large learning rate. A larger learning rate leads to larger steps, potentially accelerating convergence. However, it can also make the process unstable, especially for sensitive problems. Commonly used learning rates often range from 0.001 to 0.1, with 0.01 being a good starting point for many problems. However, the optimal learning rate can vary based on the specific dataset and model architecture. Experimentation is often necessary to find the best value. By carefully tuning the learning rate, we can balance the speed and stability of the learning process, ultimately achieving a well-fitted model. Now, let's delve deeper into the update rules for weights in gradient descent. First, let's recall the cost function we're working with. This function measures the average squared error between the predicted values, wx caret I plus b, and the actual values, y caret I, for all m data points. To find the partial derivative of j with respect to w, we'll treat b as a constant and apply the power rule. We differentiate by reducing the power and multiplying it by the function and multiplying by the derivative of wx, which is x. Similarly, to get the partial derivative of j with respect to b, we'll treat w as a constant. We differentiate by reducing the power and multiplying it by the function and multiplying by the derivative of b, which is 1. Now that we have the derivatives, we can update the weights and bias using the gradient descent update rules. See this nice 2D animation to minimize the cost function. We want the model to adjust its parameters, weights and bias. We'll focus on the weight, W, for now, and the bias, B, follows a similar process. Imagine this as a ball rolling downhill on a landscape. To guide this ball downhill, we use the derivative of the cost function with respect to W. Partial differential J, partial differential W. This derivative tells us the slope of the landscape at a specific point. The negative sign ensures we move downhill on the cost function landscape, opposite direction of the slope. Knowing that alpha is a positive value, we should take care about the sign of the derivative. A negative derivative indicates a downward slope, So we want to move the weight in that direction to decrease the cost. Negative multiplied by negative is positive, so we are adding a value to the current W. The update moves W to the right, increasing it. A positive derivative indicates an upward slope. So we want to move the weight opposite to that direction to decrease the cost. Positive multiplied by negative is negative, so we are subtracting a value from the current W. The update moves W to the left, decreasing it. Now, let's visualize the gradient descent process in 3D. Here, we have a 3D plot where the x-axis represents the weight, W. The y-axis represents the bias, B. And the z-axis represents the cost function, J. The surface you see is the cost function. Our goal is to find the lowest point on this surface, which corresponds to the optimal values of W and B. We start at a specific point on the surface, which represents our initial guess for W and B. In our case, W equals 1 and B equals 1. Gradient descent takes us on a journey downhill on this surface. The red arrows show the steps taken by the algorithm. Each step is guided by the gradient, which points us in the direction of steepest descent. As we continue taking these steps, we gradually approach the lowest point on the surface. This point is W equals 2 and B equals 3. By visualizing the process in 3D, we can better understand how gradient descent works and why it's an effective optimization technique. Now, let's see the final results of our model. Based on the gradient descent process, we found the optimal values for the weight, W, and bias, B, that minimize the cost function. These are the parameters that define the best fit line for our data. The equation for this best fit line is displayed here, which is f(x) equals 2x plus 3. We can see the best fit line plotted on the graph along with the original data points. Here's a closer look at how well the model fits the data. The red lines connecting the data points to the line represent the error between the actual grades and the grades predicted by the model. The shorter these lines are, the better the model fits the data. In this case, we see a good fit with most of the lines being relatively short. Overall, our model has successfully learned a linear relationship between the independent and dependent variables by minimizing the cost function through gradient descent. The model has learned that for every additional hour of study, the final grade is expected to increase by 2 points, with a baseline grade of 3 even without studying. Remember this table. After applying gradient descent, our model has improved significantly. The new values for W and B have led to a much better fit, as evidenced by the reduced errors in the table. In this way, our model can predict the labels for the input-only data accurately. Now, let's summarize the key concepts we've covered in linear regression with gradient descent in this video. The core equation for linear regression is simply a straight line equation. As you recall, this equation represents the best fit line through our data points, where W is the weight and B is the bias. We also explored the squared error cost function, which measures the overall error between our predicted and actual values. Gradient descent aims to minimize this cost function. Finally, we saw the gradient descent update rules for both weight, W, and bias, B. These rules allow us to iteratively adjust the model parameters to minimize the cost function and achieve a better fit for the data. By understanding these key equations and their roles, you have a solid foundation for using gradient descent in linear regression. Thank you for joining me on this journey through linear regression and gradient descent. I hope this video helped you gain a deeper understanding of these fundamental concepts in machine learning. While linear regression is a powerful tool, it's important to remember its limitations. It's best suited for linear relationships between variables. In future videos, we'll explore more complex models like polynomial regression and logistic regression to handle non-linear relationships and classification tasks. To solidify your understanding and see these concepts in action, I'll be creating a series of videos where we'll dive into the code and implement linear regression from scratch using Python. We'll also compare the results with popular machine learning libraries to see the power of both approaches. The beautiful animations you saw in this video were created using a fantastic library called Manim. If you're interested in creating your own educational or explainer animations, I highly recommend checking out Manim. There's a great community and resources available online. Want to stay updated on new content? Click the subscribe button and hit the notification bell. Prefer learning from text? Download the free PDF slides summarizing the key concepts of this video by clicking the link in the description below. Interested in the Manim code used for this video? You can purchase it and explore the animation magic yourself. Link in the description. Curious about exploring more in machine learning? Awesome! Leave a comment below if any concept needs further explanation, and I'll be happy to help. There are also great resources online you can check out. Additionally, if you're interested in applying your machine learning skills and potentially earning money, check out the links in the description below for websites like Happened and Go AI where you can train AI models. Thanks again for watching. See you in the next video.
People say you have to have a lot of passion for what you're doing, and it's totally true. And the reason is because it's so hard that if you don't, any rational person would give up. It's really hard, and you have to do it over a sustained period of time. So if you don't love it, if you're not having fun doing it, you don't really love it, you're going to give up.